Okay, so I'm going to change gears a little bit now, and I was asked to talk about what's going on with neutron scattering in high pressure applications and earth sciences. And there's a lot going on at Oak Ridge. We have a fairly growing high pressure program. And I put Bianca Haberl's name here. I'm obviously not Bianca, I'm Chris, but Bianca is leading the high pressure efforts across multiple instruments at both the SNS and HIFR, and I'll talk about that in a second. And I'm basically working at the SNAP diffractometer, which is a dedicated high pressure instrument that's been built at Oak Ridge. So if you look at Oak Ridge, we have two major neutron scattering facilities. One is the spallation neutron source, which is in the upper left. And this has been operating for probably 12 years now. And it has a number of instruments. So it's a time of flight source. So it's a proton accelerator, slams protons into a mercury target and generates neutrons. And then we have instruments around that target. The second facility that we have is the high flux isotope reactor. And this is a nuclear reactor that generates a continuous source of neutrons. And it's been upgraded in the past 10 years. All the instrument suite has been upgraded, but it was started in the 1960s as a research reactor. So when we talk about neutrons, there's some things that we have to clear out of the way pretty soon up front, and that is that neutron flux is very low compared to X-ray facilities. It's several orders of magnitude less. So this requires large samples, and generating significant pressure on very large samples is a tough thing to do. The diamond anvil cell technology has been developed for quite some time now, but the typical diamond anvil cell sample size is way too small to use for neutron scattering. So a lot of our effort has gone into scaling up diamond anvil technology to make the samples big enough so that we can see a signal from the neutrons that are scattered. However, neutrons are sensitive to a wide range of properties, both magnetic and structural. So the magnetic moment of atoms interact with neutrons, so we can get a direct measurement, both elastically and inelastically, of the magnetic structure and magnetic dynamics of the material. Also, the cross sections are comparable across the periodic table. So unlike X-rays, which scatter from electron density, neutron scattering is a nuclear process, and you find that even very light elements have a relatively high scattering cross section. So what this enables us to do is pick out the structure of light elements, and particularly pick out the structure of light elements in the presence of much heavier elements. And this is sometimes challenging when you're working with X-rays. So this is a list basically of the instruments at both facilities: the spallation neutron source, the upper left, and the HIFR reactor. And one of our aims is to take high pressure technology and bring it to many of these different types of instruments. So in particular, I'm going to talk about 3 instruments today, but we're trying to bring this technology to many more instruments. Give you an example: general purpose sands down here in the lower right, and a biosands instrument. And we have the neutron backscattering spectrometer, which I'll give an example of, and that is used to measure diffusion in materials. Vibrational spectroscopy: this is a chemical spectroscopy instrument that's used to look at phonons in crystal lattices, all the way out to the higher frequency molecular vibrations. And then we have a dedicated diffraction instrument, which is the SNAP high pressure diffractometer. And the first examples that I'll give are from the SNAP instrument. It's worth saying that SNAP, the high pressure diffractometer, is the only dedicated high pressure instrument at both of these facilities. So what that means is that none of the other instruments are optimized specifically for high pressure studies. So what we're having to do is then retrofit high pressure devices to go into instruments that weren't necessarily designed for. That having been said, we do have a number of pressure devices that are capable of various pressure ranges, various temperature ranges. As I said, we're working on a diamond anvil cell project to make diamond anvil cells samples big enough for neutron scattering. We also have recently developed a gas intensifier. We also have a gas loader for gas loading the diamond anvil cells with various inert gases, but also for hydrogen, because neutron scattering is particularly sensitive to hydrogen, it being a light molecule. Is oftentimes difficult to look at with X-rays, as I've said. So our gas loader is capable of loading about 2.5 kilobars of hydrogen into a diamond cell. Beryllium clamp cells, lower pressures, 2 GPa. Cubic anvil cells, 7 GPa. Paris Edinburgh cells, this was specifically designed for neutron scattering in Europe at the ISIS neutron source. And we look at 10 to 20 GPa with this device, and I'll talk about that a little bit in a bit. And a mini MIC-1 cell, this is a very small design of the standard MIC-1 cell, which is good for a couple of kilobars. So here's what I'm going to talk about. I'm going to give a little bit about the SNAP instruments and our recent experiments in the megabar pressure range with neutron diffraction, neutron spectroscopy on fission in the diamond anvil cell, and quasi-elastic high pressure neutron scattering on an instrument called BASIS. So to go over the capabilities on SNAP, this is a list of pressure devices, and it gives their maximum pressure range and temperature range. So sub 10 Kelvin, we can do up to slightly larger than 1500 Kelvin. When it comes to diamond anvil cells, we advertise 40 GPa as a standard reachable pressure. However, we have had several experimental runs recently where we've gone to a megabar, very close to a megabar, and over a megabar. And with our cryostats, 10 Kelvin to above room temperature. So the SNAP instrument is here. This is the team that are looking at the very high pressure experiments on SNAP. Reini Bowler joined us probably 5 years ago from the Carnegie Institution. Malcolm Guthrie is now a staff member at ORNL. And then this is the SNAP team, the instrument scientists and technicians. So this is the SNAP instrument. It looks a lot like an X-ray instrument. It's got 2 large area detectors. The sample is mounted on a hexapod. And in the cryostat here is most likely a diamond anvil cell. And there's a large closed cycle refrigerator to cool that. And then I'll explain the diamond anvil cell design a little bit more in a minute. So the neutrons come in here. This is a focusing guide that can focus the neutrons down to about 1 millimeter. Focusing neutrons is difficult. They don't have a charge. So as this is the standard workhorse diamond anvil cell at SNAP. There's a press which is driven by a gas most often helium. And this press, then you can recognize all these components, the two diamonds, the press drives the diamonds. We can go to about 8 to 10 tons with this press. The diamonds are, the diamond culet size is very large for a diamond. It's on the order of 1 millimeter. It could be 700 microns if we go to very high pressures, but 1 and 1.5 millimeter culets are very common. These are chemical vapor deposited anvils. With this one is a 9 millimeter anvil, and it's got a conical seat. So the seat is supported. Here's the culet. This is the seat. So typically the seat is supported by being pressed into a cone, or the diamond is supported by being pressed into a conical seat. This makes alignment very difficult. Everything has to be perfect. All the angles have to be perfect, or else the diamond breaks. And these seats then go into the cell, and then the neutron beam. So this cell is then flipped on its side. The neutron beam comes in here through a collimator that typically collimates the beam down to about 400 to 500 microns. So here's Riney and Bianca working on prepping a cell for a neutron experiment. The design relies on precision machining of the cell body for alignment. And oftentimes this causes a binding of the cylinder in the diamond cell. So Riney has been working on a new design of cylindrical bearings that help move the piston back and forth. And actually, this provides very stable alignment. And most recently, we did experiments on ice up to 92 GPa and got good quality diffraction data using this type of design. We're starting to go back to flat seats, however, and as we increase as we modernize the instrument a little bit with better focusing, we're finding that we can go to smaller samples, so we go back to flat seats. But in this experiment, we're looking at nickel, and we've gone to almost 120 GPa with this experiment. Of course, we still use the Paris-Edinburgh cell, which has large anvils. This is tungsten carbide anvils, and the sample volume is about 80 cubic millimeters. It's a sphere. The anvils are excavated out. This is the Paris-Edinburgh cell in the cryostat setup, which we use liquid nitrogen or a CCR, but we almost exclusively use liquid nitrogen now, where we clamp nitrogen channels around the anvils and we pass nitrogen through, and we're just cooling the anvil. And then the hydraulic oil in the press is kept warm by heaters. As a scientific example, with the Paris-Edinburgh cell, this is an experiment of a couple of years ago, but we were able to look at amorphous ice, which typically, once you pressurize ice at low temperature, you go through a series of amorphous transitions, and then you get various amorphous structures that come out of this. I'm not going to belabor the point. However, with this recent experiment, we did a very slow experiment with pressure breaks for a few hours at each of these points. And what we noticed was that we could bypass the amorphization of the sample and create a group of crystalline structures. And these are actually, this is the new phase diagram of ice at low temperature, where we see the lowest energy crystalline states now. And these turn out to be antiferroelectrically ordered states. So if you imagine the water molecules their dipoles are in different layers, are antiferroelectrically ordered. I go on to vision. This is an instrument that's not designed to do a high pressure experiment. However, it is a very efficient inverse geometry vibrational spectrometer. This is the one that looks at vibrations in molecules. all the way down to lattice modes and phonons, even down to the acoustic region. So we have a white beam that comes in from the left onto the sample, and then the energy analysis is done in the scattered beam, in the scattered neutrons are reflected off analyzer crystals, and then you get a constant energy transfer. And because it's a time of flight, you can then back out the vibrational spectrum of the sample. But if you look at the instrument, at the top here, if you can see my cursor, this is where the sample goes. So the sample actually goes down in a hole and is suspended from a flange. And there's virtually no positioning capability of the sample. You have to realize that most times in neutron scattering, samples are cubic centimeters, and beams measure centimeters in dimension. So this illustrates the challenge of doing a diamond anvil cell experiment when the diamond cell is suspended from a flange and basically put down in a manhole.
1 minute.
But you can collimate the beam to be very small, and then you can use absorbing materials to just define the beam that's going between the anvils. Again, this is challenging work, but we have designed a diamond anvil cell to do this. And as I said, this is basically, the design of this basically matches the design of the instrument. So there's no real way around that. The neutron beam comes in through the gasket in this case, and then the analyzer crystals are 120 degrees out of the plane. So that's why this cell is such an open design. We use both Versamax anvils and single crystal anvils here, and the sample is typically cooled to 5 Kelvin with a 2 cubic millimeter sample. And this is an example of hydrogen in vision under a little bit of pressure. And here you're looking at energy transfer. So this is basically the phonon density of states. And here you have the acoustic phonons, and you're going out into the lattice modes here, and you can see the shift in the lattice modes as you increase the pressure. So next we aim to increase the pressure further, and we have a plan to collect data in roughly the 10 to 15 GPa region. This is my last example now. This is the basis quasi-elastic scattering instrument. So this is meant to study diffusion in samples, particularly hydrogen diffusion. And here we've adapted the Paris-Edinburgh cell to a suitable geometry for quasi-elastic measurements. And so here's the Paris-Edinburgh cell. And to do the measurement, we actually have to have an annular sample. We don't, because of multiple scattering corrections and effects, we don't want a bulk sample in the middle. We'd rather have a very thin-walled annular sample. So this was a specially designed gasket to do that. And the groove is about 150 microns. This gasket then goes between the anvils. And here's an example of having to suspend your pressure device from a flange. So this is the flange that goes into basis, and the sample is probably 1.5 meters below the flange. And there's the Paris-Edinburgh cell. You know, this cell weighs probably 30 kilograms. And as you can see, there's virtually no ability to move the sample for alignment purposes. But here you can see the effect of quasi-elastic scattering up to over 7 GPa. And this is an elastic line here, and the quasi-elastic effects come through a broadening of this line with an additional Gaussian component that is then separated from the elastic signal and then analyzed to determine diffusion within the sample. So on this instrument, we can look at timescales from 25 picoseconds down to 16.9 picoseconds as the pressure goes up in this particular sample. So in conclusion, high pressure neutron scattering is growing, particularly at ORNL. If you look around the world, there's dedicated high pressure beam lines at the ISIS facility in the UK. There's a dedicated high pressure beam line at J-Park in Japan, and other facilities are being built. The Chinese spallation source will have a high pressure diffraction beam line. We have a variety of pressure cells and capabilities. Of course, the SNS and HIFA are user facilities, so we have user calls for beam time. If you want to use the instruments, you can contact myself or Bianca, and we continue to develop and adapt techniques for high pressure neutron scattering. So there's a website that describes the entire neutron scattering facilities at ORNL. And if you dig around in there, you can find the pressure capabilities. But I encourage you to go if you're interested. If you have a problem that you think neutrons can help you solve, then go to this website and contact myself or Bianca or Antonio, and we can set you up with a high pressure neutron program. And that's the end of my talk.
Thank you, Chris.